Welcome back to section 5 of chapter 4. In this section, we are going to be looking at linearization, sensitivity, and differentials. Now, the biggest piece here is the linearization part. The other two kind of go right along with it, but linearization, there's always questions on the AP test about that, and it's one of the big uses of calculus. So our learning targets, we can find linearizations of functions at given values. We can use linearizations to approximate expressions. We can find differentials and use them to estimate error measurements. We can answer questions involving absolute, relative, and percentage chains. And then we can solve applications using linearizations and differentials. So, the very first question is, what is a linearization? A linear approximation. So what happens, we have a function. Let's say our function looks kind of like that. We can find a tangent line to the function. We've been doing that for quite a while. So if we find a tangent line right about here at this point, we could use that line to approximate values that are close to the x value. Now, in this case, since it's curving down, it has that negative concavity. Our estimates are going to be a little bit high, but as long as we stick close, it should still give us a pretty good estimate for something that we wouldn't necessarily be able to figure out on our own. Now, if we were trying to go out here, that would give us, we'd have an estimate, but we'd be a little ways off. So you want to make sure you stay close. The definition of linearization, so if f is differentiable at x equals a, then the equation of the tangent line, L of x equals f of a plus f prime of a times x minus a, that's not new. We found the equations of tangent lines already. That's the same thing. The derivative is the slope. We use point slope form, and I strongly recommend using point slope form here, and I will show you why when we get to a problem. But it defines the linearization of f at a. The approximation is the standard linear approximation of f at a, and the point x equals a is the center of the approximation. So that's just a little bit of vocab. It's not horribly important. So let's see what we're doing. We're going to, I shorten the directions, use linearization to, and f of x equals 1, the square root of 1 plus x at x equals 0 to approximate the square root of 1.02. So for this, we need to make the equation of the line. For the equation of the line, we need 2 points, or we need a point and a slope. So the point, we can plug in 0, and we get f of 0 equals the square root of 1, which is 1. And then we need the slope. For that, we use the derivative. F prime of x, this is 1 plus x to the 1/2, so it'll be 1/2 times 1 plus x to the negative 1/2. And then chain rule, derivative of 1 plus x is just 1, so we're good. And then f prime of 0, we have 1 to the negative 1/2, that's 1 over the square root of 1, which is 1 times 1/2 is 1/2. So our linearization, and we could use y equals, we could use L of x equals. Either way, we just don't want to use f of x because we already have f of x. F of x is here. A lot of times we use L of x because our function may have been called y equals. Rarely do we have a function called L of x equals. So I'm going to use y equals the y value. So 1 plus 1/2 times x minus a, or x minus 0. Sorry, that's the x value, x minus 0. So in this case, just 0. Now, that's our line. If we want to approximate this could be written as a square root of 1 plus 0.02. So x becomes 0.02. because that's where that is. So L of 1.02, or 0.02, is going to be, let's go 0.02, is going to be 1 plus 1/2 times 0.02 minus 0. I don't know why I still have the minus 0. 1/2 times 0.02 is 0.01 plus 1. L of 0.02 is going to be 1.01. So if we take the square root of 1.02, we should get about 1.01. Now, it's not going to be exact. You can find the exact value using your calculator to see what that difference is. That's one of the things that it'll have you do, is it'll find the actual difference where you do the linear approximation, find it in your calculator, find the difference. In practical use, that's not a huge skill. That's just because this is a new topic, and so it's helping to convince you and show you that, yes, this is actually really close, but it is not perfect. Let's do another one, cosine. Cosines are harder to compute. So we have f of x is the cosine of x at x equals pi over 2 to approximate cosine of 1.75. So we're going to have, we need f of pi over 2 is cosine of pi over 2. Well, cosine of pi over 2, that's straight up in the air. Cosine is 0. And then f prime of x is going to be negative sine of x. So f prime of pi over 2 is negative sine of pi over 2 is 1, so it's negative 1. So that's our slope. We have our point is pi over 2 comma 0. So we have L of x equals 0. I'll put the 0 here for now, plus negative 1 times x minus pi over 2, which we can simplify this. We don't need the 0, and we can distribute that negative 1 since it's just a negative 1. It doesn't really make much of a difference, and the cosine is not the 1.75 is not great. So that's negative x plus pi over 2. So if we want to find the approximation, and here it's just x, so L of 1.75 will be negative 1.75 plus pi over 2, and L of, or negative 1.75 plus pi over 2 is about negative 0.178-ish. So negative 0.178. Which should make sense because that's going to be a little bit bigger than pi over 2, because pi over 2 is about 1.56-ish. And so that'll be a little bit bigger, so it's a little bit in the negative. The actual value here, if we find it, is that it actually is the actual value. The cosine of 1.75 is, that was the actual cosine. So this is cosine of 1.75 equals that. I had my notes backwards. So our approximation L of 1.75 is going to be negative 1.75 plus pi over 2, which is negative 0.1792. Then it keeps going. Then let's see how far off that was. That was negative. So the difference between these two values, the estimate and the actual value, by subtracting them, was 0.0009576. So in practical applications, are we going to be, do we need to be closer than that? Probably not. That seems like a pretty slim margin of error. So that's how close we can get. And the 1.75 and the pi over 2 aren't even particularly close together. Pi over 2 is 1.57, so they're almost 0.2 away from each other. And yet those values are still super close. So the linearization provides a really good estimate. A couple more examples. Use linear approximation for the square root of 123. So the square root of 123 is going to be really close to another number, because we know the square root of 121. So if we go for a square root of 121, we do f of x is going to equal root 121 plus x, or that is the x. So f of x equals root x, and we find it at 121. So f of 121 equals the square root of 121, which is 11. F prime of x, that's x to the 1/2, so that'll be 1/2 x to the negative 1/2, which can be written as 1 over 2 root x. We'd plug in 121 to find our slope. So we have 1 over 2 times 11, which is 1 over 22, is our slope. So we've got our point, we've got our slope. L of x equals our point. So we have 11 plus 1 over 22 times x minus 121. So it just goes right into the point slope equation. Now, this is why we use the point slope form, because now we're going to plug in our new x value, which is 123. L of 123 is going to be 11 plus 1 over 22 times 123 minus 121, which this should always be a pretty small number when you subtract that. So it'll be 2 times 1 over 22. 2 times 1 over 22 is 1 over 11. So we have 11 and 1/11, which would be 11.01010. 11.09090909, which, if we looked at what the square root of 123 was, we get 11.0905. So it was like 0.004 off, a little bit less than that. So that could still be really close. Right? Another one, this one has a cube root. So we're going to say f of x equals the cube root of x. And we're going to use, when x equals, what's a cube root close to 123 that is easy? 125. So instead of using 121, we'll use 125. So the cube root of x is x to the 1/3. So, well, let's see. F of 125, first of all, is 5. Then f prime of x will be 1/3 times x to the negative 2/3, which could be rewritten as 1/3 times the cube root of x squared. It doesn't matter if the squared is inside or outside of the root. So we can make our linearization. L of x equals the y value, 5, plus our, oh, I didn't plug in the 125. So we plug in 125, we get cube root is 5, squared is 25, times 3 is 1/75. So we have plus 1/75 times x minus 125. Now we can plug in the 123 that we're looking for. 1/75 times 123 minus 125. So in this case, when you subtract, it'll be negative because it's a little bit before that. So it'll be negative 2. So L of 123 will be 5 minus 2/75, which is going to be 4 and 73/75, which if we were getting a decimal for this one, we'd get 4.973333333333, repeating, and the cube root of 123 is 4.9731. So again, we're off by like 0.000, like 1 something. So a linear approximation, close. I mean, these are both 2 off in either direction, and yet the linear approximation is really, really close. And we were able to estimate to some pretty good accuracy these things like, what is the square root of 123? It's not something we're going to find out. And so this is actually how they originally were figuring this stuff out. They were just getting it closer and closer and closer. Differentials. So a differential is just the changes in y and the changes in x. The small changes, like the dx and the dy, are differentials. I love this equation. Dy equals f prime of x dx. Well, if we divide by dx, dy over dx equals the derivative. Yes, the derivative does equal the derivative. It's kind of multiplied over, kind of like in the implicit differentiation steps. But the dy and the dx are just small increments of x and y. So what this looks at is if we move over like by 0.01 in x, what is dy going to be? Like, how does that move? And that's all the differentials are. So if we wanted to find the differentials dy and evaluate dy for the given value of x and dx, so like for a, we have y equals x to the 5th plus 37x. So y prime would be 5x to the 4th plus 37. So what this says is that dy equals 5x to the fourth plus 37 times dx. And now we can plug in 1 for x and 0.01 for dx. So if we plug in 1 for x, we get 5 times 1 plus 37 times 0.01. 5 plus 37 is going to be 42 times 0.01 means that dy is 0.42. So when x equals 1 and we move over by 0.01, y is going to increase by about 0.42. Now it's not exact. This is kind of a linear approximation thing, because what it does is we have our curve, and then we have that tangent line, and we have dx, we have dy. So it's giving us that value, not the exact value, but the estimated value from the linear approximation, which, as we found, was actually pretty close. But this isn't giving us the value, this is giving us the change in values. Basically the same thing. So here, if, actually we know, we were at x equals 1, and so the y value is changing from about 40, like if we plugged in 1, we would get 1 plus 37, which is 38. The y value is changing from about 38 to 38.42. That's all that really means. So we have a couple more we can do. B, y equals sine of 3x. So y prime is going to be a cosine. We're going to have 3 times cosine of 3x. That 3 is there because of the chain rule. You cannot forget about the chain rule. And x is pi, and the dx is that. So dy will be 3 cosine 3x dx. So dy equals 3 times cosine of 3 pi times negative 0.02. So cosine of 3 pi is going to be the same as cosine of pi, which is negative 1, times 3 is negative 3, times negative 0.02 is going to be positive 0.06. So dy, the change in y, when we're going to the left, 0.02 to the left, when x equals pi, is going to be about 0.06. And then C, x plus y equals xy. So we need to find y prime, which means this is implicit. This is a dx plus dy equals x times y is going to use product rule. You might have figured this one out already. X dy plus y dx. We have x times y a lot. It's x dy plus y dx. We can move the dy's over. So we'll have a dy minus x dy equals y dx minus dx. We can factor out the dy. 1 minus x dy equals y minus 1 dx. And so then we can divide the 1 minus x. Dy equals y minus 1 over 1 minus x dx. That is the dy equals the derivative, y minus 1 over 1 minus x, times dx. We don't need to divide the dx over in this case. And now we need x equals 2 and dx equals 0.05. So we have y minus 1, we'll figure out y in a second, over 1 minus 2 times 0.05. So now what does y equal? Well, plug in 2 back into that original equation. We have 2 plus y equals 2y. If we subtract the y over, we get 2 equals y, so y equals 2 as well. So we have 2 minus 1 is 1 over negative 1. That's just negative 1. So dy equals negative 1 times 0.05 is negative 0.05. So that's really all there is to differentials. It's just what is the change of y when you have a change of x? You the differential estimate of change, it's the same thing, but instead of y equals, they're using df. Other than that, it's the exact same thing. It's a change in the function instead of the change in y. Sensitivity analysis. Sensitivity is just how much does y change when x changes. It's like what we've been working on. It's just, this is where we can find the estimated value and find the actual value and then subtract them to see what that difference is. So this is another great equation. Delta y is about equal to dy over dx times delta x. Yeah. So problem here, we have a circle. Radius r increases from 10 to 10.1 meters. Use the linearization to estimate the increase in circle's area, and then compute the estimate, or compare the estimate with the true change in the area to find the approximation error. And so obviously with the approximation error, we want that to be small. So we know that the area equals pi r squared, and r equals 10 delta r, or dr, equals 0.1. So the dA will be 2 pi r times dr. And then we can, so the change in area will be 2 times pi times the radius, which is 10, times 0.1. 10 times 0.1 is just 1. So the change of area, that differential, is 2 pi. All right, so that's finding the differential. That's what we just did. Now find the actual change. The actual change is going to be the area at 10. So that'll be pi times 10 squared minus pi times 10.1 squared. And so when we do this, 10 squared is going to be 100 pi. Now we should probably flip these. Negative 100 pi plus, since the 10.1 is going to be bigger, 10.1 squared is 102.01. And when we subtract 102.01 minus 100, we get 2.01 pi. So that's the actual change. So the estimated change is 2 pi, actual change is 2.01 pi. The sensitivity is just looking at what that difference is. Now, there are a couple different things that we can find with this. So before we get too far, I'm going to go dA equals 2 pi, and then actual was 2.01 pi. So we have different things. We have absolute change. That's what we just found. The true was at 2.01 pi. The estimated was the 2 pi. That's the absolute change is the actual change of y values. The relative change. So the relative change is going to be how much it changed versus the original value. So the true one would get, this actual is delta f, so it would be 2.01 pi divided by what was the area from 10. It was f of 10, so that would be pi times 10 squared, which was 100 pi. And so the relative change was, so pi's cancel, we divide, we get 0.0201 is the relative change, and that's the true relative change. If we go down to the percentage change, so let's see, this is relative, I'll label, and then percent, we just change that into a percent, 2.01%. It grew by 2.01%. The estimated change, we have the derivative divided by f of a times the delta x. So remember, the derivative times the delta x is what we had here. That's the derivative times the delta x. And then divide by that original thing. So our relative change here is going to be 2 pi divided by the 100 pi, that original area, which is just 0.02. And then the percent, again, we multiply by percent, so it's just 2%. So we estimated that we're going to gain 2%. In actuality, we gained 2.01%. It's just another way of looking at the different things. So most of what we've done, the differentials and all that, that is just straight absolute change. That was the linearization. We found the estimate. For the true value, we actually had to find the true value. And so those are the differentials. And then for the relative and percentage change, we just saw, it's like, all right, so we had to change, like this was the difference. Well, how big was it? It was that much out of this much, so it was only a 2% change, or 0.02 probability, or a relative change. So again, linearization is the big topic here. The other pieces just kind of come from that. It's a little bit of analysis of the linearization process itself, but the actual ability to linearize a part and then make estimates, that's the key point here. So I will see you in class where we will practice this, but until then, keep working problems, keep asking questions, and as always, happy mathing.